you ever looked up at a building and wondered how tall does a building have to be before it is considered a high-rise? A high-rise building is a tall, multi-story structure commonly found in contemporary metropolitan settings and is designed for residential, commercial, or mixed-use purposes. By constructing it vertically rather than horizontally, this helps to maximize space in cities with limited space and high population density. Although there is no universally agreed definition, a high-rise building is generally considered to begin around 7 stories or approximately 75 to 100 feet in height. Rapid urbanization and a limited horizontal space in cities are driving up the demand for high-rise buildings. They provide a practical answer by capitalizing on high-rise real estate, solving housing and office shortage, and minimizing urban sprawl. In addition, it also promotes economic growth, attract investment, and contribute to the development of efficient urban environments, with many incorporating sustainable design features that address environmental concerns. In terms of structural design, high-rise building foundations must often carry significant gravity loads and are typically made from consistent of concrete piers, piles, or caissons lowered into the earth. Solid rock beds are the ideal foundation, although it is possible to distribute loads evenly even on relatively soft ground. The most essential factor in construction of high-rise structures is their ability to withstand the lateral stresses imposed by the winds or potential earthquakes. Most high-rise frames are built of steel or steel plus concrete. Their frames are made of columns and beams, and cross-bracing or shear walls can be utilized to provide a structural frame more lateral rigidity to withstand wind loads. Along with their structural design, high-rise buildings serve various functions including offices, residential apartments, hotels, and mixed-use developments. A high-rise building is more than just a tall structure. It is a key response to expanding urbanization needs. As cities rise vertically because of limited land and growing population, they effectively optimize area for dwelling, commercial, and retail beyond their functional role. These structures are economic drivers to the economic development and have the defining features of a modern city skylines.
So now I'm going to briefly explain about our case study, which focuses on Merdeka 118. It is located in the heart of Malaysia, Kuala Lumpur, and formerly known as the Menara Warisan Merdeka. It has 118 floors and stands 678.9 meters tall, making it the tallest building in Malaysia and also the second tallest building in the world after Burj Khalifa. The construction was completed in November 2023 and was officially opened to public on the 10th of January 2024. The project was announced by the former Prime Minister Datuk Sri Abdullah Ahmad Badawi in 2007. It was developed by Permodalan Nasional Berhad (PNB) and through PNB Merdeka Ventures Sendirian Berhad, while Samsung C&T and UEM Group joint ventures served as the main contractor. So now, the building was designed by the vendor Katsalidis in collaboration with RSP Architects Sendirian Berhad. Its unique glass facade is inspired by Malaysian Songket and Islamic geometric patterns, while the iconic spire symbolizes Tunku Abdul Rahman raising his hand during the Malaysia's declaration of independence in 1957. Merdeka 118 is located at Jalan Hang Jebat, close to landmarks such as Petaling Street, Merdeka Stadium, and also Stadium Negara. The building consists of premium office spaces, the Backyard Kuala Lumpur Hotel, 118 Mall, and the view at 118 Observation Deck. So, structurally, the tower uses a reinforced concrete megastructure with steel outbridges and belt trusses to provide stability. Its diamond-shaped facade is made on triangular glass panel inspired by Songket patterns, while the 120 meters perforated steel spire reduces wind load and vibration. Inside, the 30 meters high lobby is inspired by traditional Malay Minangkabau architecture and features a grand entrance for efficient visitors access. So now, that is the brief explanation. We are going to move on to the next topic.
will explain the key design requirement of Merdeka 118. There are three main design requirements for this project. The first requirement is structural stability and the foundation system. Since the soil in Kuala Lumpur is soft in some areas, the building used a deep foundation system to support its heavy load safely. Engineers also combine steel and concrete to provide both strength and flexibility for the structure. The second requirement is resistant to wind and earthquakes. Because the building is very tall, it must be able to resist strong winds. The tapered shape and curved facade help reduce wind pressure and improve the building's stability. Wind tunnel testing was also carried out to make sure the building remains safe during extreme weather. The final requirement is efficient vertical transportation and sustainability. The building uses high-speed lifts to move people efficiently. It also includes green features such as solar panels and rainwater harvesting system, and energy-efficient glass to reduce energy use and improve environmental performance. Overall, these key design requirements help ensure that Merdeka 118 is safe, efficient, and sustainable for long-term use.
Now, we will explore the commonly used materials and advanced construction technologies applied in Merdeka 118. As a super tall structure, Merdeka 118 requires modern construction methods to support its complex design and structural system. The selection of suitable materials and technologies was essential to ensure the building achieved high strength, stability, safety, and construction efficiency. Let's begin with high-performance concrete, or HPC. To maximize floor space and improve structural performance, engineers use high-performance concrete up to grade C105. This ultra-high-strength concrete was applied to the mega columns and core walls to withstand heavy gravity and wind loads. Extensive planning, testing, and quality control programs were also carried out to ensure the concrete met the required engineering standards. Besides the use of advanced concrete technology, building information modeling or BIM also played an important role during the design stage. Vendor Facilities architects used Graphisoft ArchiCAD to coordinate the project digitally. The building presented several technical challenges, including the integration of the outrigger system, curtain wall installation, and the connection between the structural frame and the building core. Through BIM technology, the project team was able to visualize and coordinate the building before construction began, improving accuracy and communication among architects, engineers, contractors, and clients. Another important technology used in Merdeka 118 is the glass curtain wall system. The building facade consists of a custom unitized system made from glass fiber reinforced polymer, high-performance glass, and aluminum components. The distinctive crystalline appearance of the tower is created by 8,144 glass panels arranged in a diamond-shaped pattern. Besides enhancing the architectural appearance, the curtain wall system provides weather resistance, durability, and long-term performance suitable for a super tall building. Overall, the combination of grade C105 concrete, BIM technology, and the advanced curtain wall system contributed significantly to the successful construction of Merdeka 118. These technologies improve structural performance, construction efficiency, and architectural quality, making the project one of the most remarkable skyscrapers in the world.
So now let's talk about the construction techniques used in Merdeka 118. So the first one is circular self-supporting cofferdam wall. So instead of using conventional retaining walls with the cross tracks or ground anchors, engineers built a circular cofferdam that uses hook truss to resist soil pressure. So this eliminates the need for internal bracing, creating an open excavation area and allowing heavy machinery to work more efficiently. So the second technique is the use of high performance concrete, or also known as HPC. So since Merdeka 118 is a 118-story building, it must support the enormous load and resist strong wind forces. Therefore, engineers use ultra-high-strength cast-in-situ concrete with a compressive strength of 105 megapascal. This concrete also reaches high strength within 12 hours after pouring, improving both construction speed and structural performance. Now, the third one is asynchronous core-first framework. In this method, the reinforced concrete core was constructed 12 floors ahead of the surrounding steel structure. This allowed heavy construction work to be carried out earlier, while 5-star S460M high-strength steel was installed afterward to form the floors and walls. As a result, the building's structural dead weight was reduced by 20%. Isn't it cool? And also the last technique is the core and outrigger stiffness integration. Merdeka 118 supported by 8 mega columns connected to the central core through 3 sets of 3-story outrigger trusses and 6 belt trusses. These structural elements transfer the wind-induced forces from the core to the mega column and finally to the dead pile foundation, improving the building's stability and also the reducing sway caused by the strong wind. So we have done with construction technique. We are going to move on to the next topic.
Now we'll get into the method of construction and specifications applied. Number 1. Site preparation and excavation. The Merdeka 118 used an embedded retaining system for excavation with an 800mm thick circular cofferdam wall surrounding the tower's footprint to minimize any settlement or lateral movement located between the transport hub in KL Centra and TRX precinct. Number 2. Foundation works. The tower uses big bore piles anchored into the ground by a 2-meter diameter reinforced concrete piles, which protect it against gravity, wind, and mild local tremors. 337 reinforced concrete pillars form the foundation. For the base, Merdeka 118 uses a 4-meter raft foundation. The piles are connected to the building's central core and surrounding mega columns by a large base high-performance concrete with a strength of up to G105 MPa. Cement was the creation of a single-stage concrete pumping system that could reach heights up to 500 meters. Number 3. Construction of underground levels. A 3-story upper parking structure and a 5-story underground parking structure were constructed using both bottom-up and top-bottom construction techniques. This allowed for the simultaneous development of the upper basement, parking levels, and the main atrium complex without interfering with the vertical construction of the main tower. Number 4. Core construction. After the completion of the foundation works, construction of the 118-story structural system commenced. The central core was constructed first using a mechanical formwork system. This core is surrounded by 8 reinforced concrete mega columns forming the primary load-bearing structure, which is further supported by steel structure system. 4 tower cranes were installed at the upper levels to facilitate material handling and maintain continuous construction progress as the building increased in height. As construction progressed, reduced working space at higher levels created logistical constraints. To address this, a climbing formwork system was used for core construction. Formwork panels were assembled and concrete was cast for each level of the core. After curing, the formwork was lifted hydraulically along with rails attached to the core, allowing continuous vertical construction. Number 5. Structural frame erection. The tower lateral load resisting system includes 8 mega columns, a structural reinforced concrete core wall, intermediate steel columns, 6 belt truss levels, and 3 outrigger system. The core is tied to the mega columns through 3 outrigger sets in the east-west direction and 2 in the north-south direction, forming the main system for resisting wind and lateral loads. At the top of the tower is completed with 169-meter steel spire with a varied bended form designed to reduce wind forces and improve aerodynamic performance. Number 6. Facade installation. The pre-designed steel frame system was precisely fitted to thousands of facade glass panels that were put in a modular modules. Every panel had to be accurately positioned to follow the tower's tapering shape and constantly shifting curve along its vertical ascent. Installation procedures use temporarily suspended working platforms in conjunction with laser surveying technologies to get the necessary degree of accuracy. This made it possible for it to maintain strict tolerances despite the strong wind loads and structural vibration at elevations of several hundred meters. Number 7. Mechanical and electrical works. Through early stage coordination using building information modeling, or also known as BIM, platforms such as ArchiCAD, Solibri, and Econex, the design and integration of the building, electrical, water supply, drainage, central air conditioning, and fire system were effectively coordinated. These systems were organized into multiple vertical zones to accommodate variation in air pressure, temperature, and wind conditions at different elevations of the tower, a fundamental requirement for super tall structures. Number 8. Interior finishing. To ensure a durable and long-lasting bond for the finishing materials, Keraflex Maxi S1 was selected as the primary adhesive. This deformable cement-based adhesive offers an extended open time, low dust technology, and very low volatile organic compound emissions, contributing to both installation efficiency and project sustainability objectives. It was used for the installation of marble slabs in the lobby floors and bathroom areas of the adjacent shopping center development. For the stone wall finishes in the lobby, Ultracolor Plus grout was used. This low VOC polymer modified grout provide rapid setting and drying characteristics while resisting tolerances, water penetration, and mold growth, ensuring both durability and ease of maintenance. Last but not least, number 9. Testing and commissioning. Each zone has a distinct pressure zones at different altitude. Validating compliance across every square meter of the building required a non-standard certification approach. AirScan, the company that handled the verification process for pressure testing, distributed sampling stations throughout altitudes, bands, and functional zones, including lower level, mid-rise offices, and upper hotel adjacent floors. The assessment was carried out by a team of 5 over approximately 50 hours on site. During this period, intensive environmental monitoring was conducted across the building, including 9,600 air quality measurements, 500 thermal comfort readings, 150 lighting measurements, 8 hours of acoustic data, and 55 liters of water samples for laboratory analysis.
Moving on, we will now look at the machinery and equipment used during the construction of Merdeka 118. First, tower cranes were used to lift and transport heavy construction materials such as steel members and concrete elements to different levels of the building. In a high-rise project like Merdeka 118, tower cranes were essential because they allowed materials to be moved efficiently across the construction site and reduced the need for manual handling at great heights. Another important equipment used was the hydraulic jack system. This system was applied during the construction of the building spire, which contributes approximately 160 meters to the overall height of Merdeka 118. Since conventional lifting methods were limited at such elevation, hydraulic jacks were used to raise and position the upper section of the spire accurately during the final stage of construction. In addition, a high-pressure stationary concrete pumping system was used to deliver high-performance C105 concrete to extremely high levels of the building. Prior to construction, pumping tests were carried out using the Putzmeister PSA 14,000 SHP stationary pump to verify the pumping capability of the concrete mixture. The successful pumping of concrete up to 510 meters became a significant achievement for the project. Overall, the use of tower cranes, hydraulic jacking system, and high-pressure concrete pumps contributed significantly to the successful construction of Merdeka 118 by improving efficiency, precision, and safety throughout the project.
Now, I will continue with the construction challenges of Merdeka 118. The first challenges is safety and fire evacuation. Due to Merdeka 118 is a very tall building, it is not easy to evacuate people during a fire. If everyone only uses the stairs, the evacuation process will take a long time, especially when there are many people inside the building. The second challenge is cost control. Merdeka 118 is a mega project, so it requires a very large budget. Without a good planning and management, the construction cost can easily increase. And the third challenge is time constraints. The construction work was affected by the COVID-19 movement control, and it was also difficult to manage workers, building materials, and equipment, which caused delays to the project. And the last challenge is sustainability and energy efficiency. Due to building is very tall, it needs a lot of energy for lighting, cooling, and daily operations. At the same time, the project also had to reduce its impact on the environment and meet green building standards. Next, I will explain the solutions that were implemented to overcome the challenges that I mentioned earlier. The first challenge was safety and fire evacuation, and to solve this problem, Merdeka 118 used a occupant evacuation operation, or called OEO lifts, to help people evacuate the building more safely during an emergency. The building also includes a fire-resistant doors, smoke control system, emergency power supply, and protected escape routes to improve the safety of occupants. Next, the challenge was cost control. To overcome this challenge, the project used strict budget management and an open tender process to reduce unnecessary costs. And the third challenge was time constraints caused by the MCO and project coordination. To solve this problem, the construction team followed strict SOP, arranged work in different shifts, and used digital tools such as building information modeling, or called BIM, and Connects. This tool helps improve communication, reduce delays, and keep the project on schedule. The final challenge was sustainability and energy efficiency. To address this challenge, Merdeka 118 was designed with the green building features such as energy efficient glass, solar panels, daylight sensors, an efficient cooling system, and a rainwater management system. These features help reduce energy use, save resources, and support long-term sustainability.
Merdeka 118 proved significant advancement in Malaysia's building technology through the successful construction of a skyscraper, despite having uncommon challenges, which the site was posed by a karstic limestone geological formation. It had been overcome through adaptable geotechnical engineering. At the same time, innovations in material science and high-pressure concrete logistics were developed to align with the strict requirements to ensure structural stability. Despite having a complex design, which is inspired by traditional songket patterns, it was overcome using the cloud-based Building Information Modeling (BIM) platforms. At the same time, this proves that these platforms are essential for resolving spatial conflicts among various disciplines and ensuring project continuity even when faced with environmental disruptions. Furthermore, Merdeka 118 serves as a clear model for vertical urban development. It demonstrates that future megastructure can honor local cultural stories while leading the way in sustainable, high-density engineering practices that push the technical limits of modern construction. To conclude, Merdeka 118 not only represent a pinnacle of architecture and engineering achievement, but also set a precedent for future projects worldwide. By harmonizing advanced technology with cultural elements, it exemplifies how modern skyscrapers can be both functional and reflective of local heritage. As urban population continue to grow, the lessons learned from Merdeka 118 will be crucial in guiding the next generation of high-rise developments, ensuring that they are not only resilient and innovative, but also deeply connected to the surrounding and communities.
Thank you for watching.
Bye for real.